guess it's 11 o'clock, so we'll begin. This is the medical statistics sessions. We have 5 speakers today speaking on a wide variety of topics, but we have a pretty quick transition between each of the speakers, so I'm going to let them introduce themselves, which is a little bit of a relief to me because some of the names would be difficult for me to pronounce, although I do my best. My name is Janine Harris, and I am moderating the session, so I'd be happy to answer any questions about the session. I will be holding up signs for the speakers at 3 minutes and 1 minute. Each speaker will talk for about 15 minutes and then have 3 minutes for questions, which is probably not a ton of questions, so I'm sure they'd be happy to stick around after the end if you have something you don't get answered during the talk. So I will now introduce our first speaker for today, which is Sebastian Mayer, speaking on social contact data and endemic epidemic models and probabilistic forecasting with surveillance.
Welcome. I think this is the first of 2 talks in this session bringing together social contacts and infectious disease spread. But I definitely don't hope that this in any way affects your conference experience here at the useR. So, epidemic models have 2 distinct roles. One is understanding, support of the understanding of infectious disease spread. The other one is forecasting. For the latter, the World Health Organization in 2014 said that forecasting disease outbreaks is still in its infancy, however, unlike weather forecasting, where substantial progress has been made in recent years. And our aim my aim with this talk is to transfer some of this progress to the forecasting of infectious disease incidents. There are some key requirements for this. So first, a multivariate view is required to forecast infectious disease incidents in different regions and subgroups, because infectious diseases spread, so different subgroups might be affected differently by the infectious disease, and also different regions might suffer in a varying range from this disease. Secondly, you need the data, suitable data. This would mean data from routine public health surveillance containing counts of reported cases of infectious disease, and this data should be stratified, so at least, say, by region and by age group. Then, for useful forecasts, you need statistical models which quantify the uncertainty attached to the forecasts. And last but not least, to select among potential candidate models for forecasting, you need tools for predictive model assessment. So now I will first sketch the different dimensions of infectious disease spread before applying a specific model to norovirus gastroenteritis in Berlin. This application is contained in an R package, which is on CRAN now. It's called HHH4 contacts, and you can use this package to reproduce some of the results presented here. I won't show all the code. So, as the title of the talk says, infectious disease spread is associated with social contacts. There was a large EU-funded, so we are Brussels, so this, I have to say, it's an EU-funded study. It's called Polymod, and it measured the contact rates among subgroups of the population. And what you see here is an age-structured contact matrix where you have the age group of the participants on the y-axis and the age groups of the contact persons on the x-axis. We see that there's a predominant contact pattern on the diagonal, so people tend to mix with other people of the same age. And there are these off-diagonal patterns which reflect the contacts from the parent generation to to their children, here and here. And we see that there's an especially intense amount of contacts in the age group of the school children. So they tend to have more contacts with each other, and this is where also most infectious diseases I'm concerned about spread, so within schools, for example, or child care centers. So and these contact patterns were remarkably similar across European countries. This is described in their publication. Okay. So the next dimension is space. This means location and distance. So there's Tobler's first law of geography, just saying that everything is related to everything else, but near things are more related than distant things. This is quite vague, but we can make this more precise because it seems that human travel, the distance traveled by humans within a few days, is distributed as a power law. And this distribution of human travel seems to translate to the spread of infectious diseases. So this is shown here is a power law kernel, which should indicate that, so if I'm close to this infectious person at this location, I'm more likely to get infected as well. And if I'm more, but there's also some risk of transmission across larger distances because this power law has a heavy tail. So if people use planes to fly to the useR conference, then there is also some risk of transmitting this disease over large distances. So this is about distance, and the other thing is, of course, there are environmental risks associated with place. So there might be increased risk of transmission within cities compared to rural areas. The last dimension is time. Of course, infectious diseases only have most of the time, most infectious diseases have a limited infectious period, which means the number of infectious people here in red can increase when the outbreak starts, but then it can decline again because people become recovered. Then it can increase again. So this infectious period is limited. There are maybe occasional outbreaks. This is a plot of a closed population outbreak where at the end everyone in this population got infected. And another aspect of time is seasonality. Many infectious diseases occur mainly in winter, like influenza and also norovirus. So there's some kind of seasonal effect within the year. Okay, so now I will present the data on norovirus, gastroenteritis from Berlin. Many of you may know this disease. It doesn't have very nice, appealing symptoms. So you start vomiting and get abdominal cramps, and this doesn't last very long, but it's very heavy and it is highly contagious. And there's no vaccination available for this disease. So here we see data from Berlin during 5 years, stratified by age group. We see that there's a high incidence among the children from 0 to 4 years. We see the seasonality, which peaks during Christmas time, actually. And in red, you always see the last weeks of the year, because then we have a reporting deficiency during this Christmas break. So there are usually less cases reported in this period. And we have lower incidence, or lower reported incidence at least, in the other middle age groups, and again more incidence among the oldest. We can also see that there seems to be a shift in seasonality. The children peak earlier than this red line, and the oldest people peak. The outbreak is later, somehow later. Okay. So I present the idea of an age-structured spatiotemporal or areal time series model here, just in short. So the basic idea that the mean incidence decomposes additively into two components. The green component is the so-called endemic component, which accounts for infections not linked to other observed infections. So somehow the background risk of getting infected. And the other component is the main component. So this is the autoregressive part. Here you see the counts denoted by Y, in an age group G prime, in region R prime, in the previous week T minus 1. And these previous counts are weighted by 2 separate weights. And I sum over all these other age groups, and then I get the mean incidence in the current age group G in region R in week T. So now for these components. So there are these 2 log linear predictors. This is like in regression modeling. I can put covariates here. I can put population offsets, so where there's more population, there are more cases, naturally. I can put in seasonality, time effects, and group-specific intercepts, like to represent that the old people have a higher incidence, and so on. I can also include vaccination coverage to reflect that in regions where people tend to have a higher vaccination coverage, then there's less transmission. So these weights denoted by C, here the contact matrix comes in. So here we want to reflect that there's more transmission from the group G prime if this contact matrix has a large value in the associated cell. So there's more transmission, for example, from within the same age group. The value of CG prime G is larger here. And the W weights are the spatial weights. And for instance, as said earlier, these could be power law weights. So with an increasing distance measured in terms of order of neighborhood between the adjacent regions, the transmission rate decreases. So predominant transmission would occur within the district of the infective, and then as the order of neighborhood increases, the transmission rate decreases. So this is measured as a function of order of neighborhood here. And this parameter here, this decay parameter, would be something which we would like to estimate. So if this would be very large, then we have a heavy decay, and the infection would spread predominantly locally. If this decay parameter would be 0, then there would be homogeneous transmission within Berlin, for example. But we actually would also like to estimate some parameter associated with this contact matrix, because we can't assume that the contact matrix derived from this large contact survey translates directly to weights in infectious disease spread models. So we adjust this contact matrix with a parameter. We adjust it by taking the contact matrix to a power kappa via an eigenvalue decomposition. What this means is, if this value of kappa is 0, we would have a contact matrix which has 1s on the diagonal, which means that transmission only occurs within each group. And a value of 1 would mean we just use the contact matrix from the polymod survey. And as kappa increases, the rows of the contact matrix get similar to each other, so this would mean that transmission is independent of the age group of the infective. And this kappa would also be estimated as part of this model. Okay, the model estimation works via maximizing the likelihood using a function in the surveillance package called HHH4. This is the main model class. And here's some code of a simple such model. So actually, the modeling is quite complex. So you really need some lines to specify the whole model. So first here's how you get the data. If you have this HHH4 context package, which contains the norovirus data, this data has as many rows as you have weeks, and it has as many columns as you have age groups times districts. So here's 72 columns. And then to fit such a model, you put in the data and you specify the model. And this contains the endemic component. Here, in a simple case, just some sinusoidal time effects and an offset for the population. And you have the neighborhood component here, maybe with a population effect, meaning that infectiousness scales with the population size of the district. Then you need to specify the spatial weights, for instance, a power law. You need to specify the contact matrix as the other type of weights. Then here goes the population, which is used in the formula here as an additional data. You specify the distribution. So you could use Poisson, but Poisson is usually not a good idea because over-dispersion, there's significant over-dispersion in surveillance data usually. So we use a negative binomial distribution. Yeah, so that's a simple model. Okay, and what we get out of this is, for example, we can look at the mean decomposition, at the estimated mean decomposition by age group aggregated over all the districts. We would see that in the oldest age group there's a considerable amount of transmission within the same age group. So people, let's say, how do they call these? In the residences for old people, I don't know the name. So there the disease spreads predominantly within the same age group. This is reflected by the large blue contribution here. The gray contribution is the endemic, the background component, which is mainly identified to reflect the spread in this age group where there's very little incidence, so it's difficult to, I think this is because of underreporting also, that you can't identify autoregressive behavior. But what we also see is that the yellow part, which is transmission from other age groups, is only visible actually in these age groups, which are the parent generations. So this would indicate that there is some transmission from the younger age groups to the parent age groups. Okay, so now this was an output from the most complex model, and this was selected because it had the best AIC. But the question is whether also this choice of model is also supported by the predictive model assessment. We can quantify sharpness and calibration of these probabilistic forecasts, so we can compute one step ahead forecasts and long-term forecasts. And to quantify the quality of these forecasts, we should use proper scoring rules as overall performance measures. And there's a nice review paper by Tilman Gneiting and Matthias Katzfuß, which introduces or describes these scoring rules. These scores assign a penalty score based on the predictive distribution and the actual observation. So the smaller the score, the better is the model, or the better are the predictions. Here's an example of such a score. It includes a measure of sharpness of the prediction and a measure of calibration, so the distance of the observation to the prediction. I think my time is almost over, so I only show two plots of long-term forecasts. One target quantity is the overall epidemic curve obtained via simulations from the model. Here are two models. So one model is a purely endemic model, and the other one is the full model with social context and spatial weights and so on, which leads to larger uncertainty and which is actually good if we compare the forecasts in green with the observations in dots, because the purely endemic model would not cover, the forecast wouldn't cover the actual observations, but this is true here. And the other target quantity, for instance, our final size is the final size by age group. We see again that a simpler endemic model would not cover the observations, mainly in the age group 65 plus, where the forecasts are too large compared to the actual observation. But in the full model, there's a larger uncertainty, so the model would be better calibrated. So to summarize, these models don't perfectly represent individual level disease transmission, but they are still useful for prediction of aggregate level surveillance counts. We have seen that the model fit and the predictions improve if we incorporate spatial weights and social contact data. And I want to stress that if your goal in modeling is forecasting, then you should use proper scoring rules to assess the quality of the probabilistic forecast, and not, for instance, something like correlation coefficients, which we know if just your forecasts are twice as large as the observation, your correlation is perfect, but your forecasts are really bad. So you should use scores which really deal with forecasts, with probabilistic forecasts. The package surveillance implements some univariate scoring rules, the rank probability score, David-Sapistiani score, and the log score. And for continuous distributions, there's another package recently published on RAN called scoring rules. And as an outlook, so the user interface for multivariate scoring rules is not existent in the surveillance package, so this will come. Also, HHH4 models for binomial quantities, like the proportion of patients with flu among doctor visits, which is also interesting from a public health perspective. And there will be an HHH4 add-on package by Johannes Bracher, who is developing analytical scores for multivariate path forecasts and distributed higher order time lags, which means that not only the last week is incorporated in the autoregressive component, but also weeks before that. So thanks for your attention.
We're going to hold questions to the end because we're running a couple minutes late and we want to make sure everybody can get to all the sessions that they want to see. So you can talk with Sebastian after the fact if you want to ask him anything.